let's dive into something that's literally all around us, but we barely ever think about it. Acids and bases. I mean, they're responsible for everything from the tartness of your lemonade to the cleaning power of soap. They are shaping our world in ways you might not even realize. So have you ever actually wondered, why is a lemon so sour? Or how does that baking soda and vinegar volcano trick actually work? Well, the answer to both is the exact same thing, this secret chemical dance between acids and bases. So let's pull back the curtain and see how it all goes down. Okay, first things first. Let's meet the two main characters in this whole story. What really makes an acid and a base a base? Let's find out. Yeah, you really shouldn't think of them as just, boring chemicals sitting on a shelf. They're way more like active players in a massive number of reactions that are happening every single second all over the planet and even inside your own body. Okay, so the most important difference between them, it all comes down to a really simple exchange. There's this thing called the Brønsted-Lowry theory, and it's pretty straightforward. An acid is basically a proton donor. It loves to give away a hydrogen ion. And the base, it's the proton acceptor, just waiting to catch that very same proton. This simple little game of give and take, well, that defines their entire relationship. All right, so now we know their secret identity. They're proton traders. But how do we actually spot them out in the wild? In the real world. Let's take a look at the clues they leave behind. You can totally tell them apart by some pretty clear signs. Acids, right, like the stuff in lemon and oranges, they have that sour taste. Bases, on the other hand, like baking soda, are usually bitter and feel kind of slippery or soapy to the touch. But, and this is super, super important, never taste or touch an unknown chemical to find out. Seriously, that's why scientists use safe stuff like litmus paper. For an acid, blue litmus paper turns red. For a base, red turns blue. It's a simple and way safer test. Okay, so we know what they are and how to identify them. But now for the fun part, what do they actually do? This is where their personalities really start to shine. Well, acids are known for being pretty reactive, especially with certain metals. When a strong acid gets near something like zinc or iron, it just goes to town, stripping away electrons and releasing hydrogen gas. And all those bubbles you see, that's the classic sign of the super energetic reaction happening. But the most famous reaction of all, the ultimate showdown really, is called neutralization. It's what happens when an acid and a base finally meet. They basically just cancel each other out. The end result? You get water and something called a salt, which in chemistry is just a neutral compound that's left over. It's like the perfect chemical peace treaty. So we've seen what happens when they get together. But why? Why do they do all this? Let's dig into the secret rulebook that's running the whole show, what I like to call the proton dance. Let's go back to our main definition, because it's so important. The acid is basically the leader in this dance. Its entire job, its whole purpose, is to give away or donate one single proton, that tiny little hydrogen ion. And, of course, every great dance needs a partner, right? That's where the base comes in. It's ready to step in and accept that proton. Its whole identity is defined by its ability to catch what the acid throws. And that's really it. That's the heart of the whole thing. The fizzing, the color changes, that neutralization reaction we just talked about. It's all powered by one simple move. An acid hands a proton over to a base. It's just a simple transfer, but it changes everything. So what happens after the proton gets handed off? Well, this is where it gets really cool. They pretty much swap identities. The original acid, which is now missing its proton, suddenly has room to take one back. So now it acts like a base. We call it a conjugate base. And the original base, which is now holding that extra proton, it can give it away, which makes it a conjugate acid. It's like they're before and after pictures of the same chemical, and they're always linked together as a pair. Okay, but this isn't just some abstract theory in a textbook, right? This proton dance is happening all around you right now. And it is absolutely crucial to our daily lives. I mean, think about it. Right this second, there's super strong hydrochloric acid in your stomach. We're talking a pH between 1 and 2, almost as strong as battery acid, and it's digesting your food. The soap you use works because it's a base, and that's how it breaks down grease and oil. The fertilizers that grow our food, the paper we write on, they're all made using acids and bases. And it's not just us. The health of our entire planet, from issues like acid rain to the pH balance of our oceans, depends on this chemistry. They are quite literally everywhere. So if there's one thing to take away from all this, it's this. Our world runs on a delicate balance. It's this constant, microscopic tug of war between these proton donors and proton acceptors. And this incredible equilibrium is what makes life as we know it even possible. So that really leaves us with a final and pretty critical question. We've seen just how vital this natural balancing act is. So, what happens when we, through our own activities, start to tip those scales? Something to think about.